Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's lecture examines a phase sequence detector circuit. Our objective is to discuss phase sequence and its critical role in the production, transmission, and use of three-phase AC power. We'll examine an application of unbalanced three-wire Y configuration that can be used to detect phase sequence. This lecture operates under the presumption the viewer has more than a passing familiarity with three-phase AC and unbalanced Y-configured loads, as illustrated in the Introduction to Three-Phase AC and Unbalanced Y Configurations lectures, both available at the Big Bad Tech channel. If you haven't watched these lectures yet, or only didn't recall their contents, please take the time to do so now. You are no doubt aware that a three-phase AC system is characterized by three voltage waveforms with the same magnitude and frequency offset from each other by a relative 120 degrees. A common light industrial three-phase AC system available in the United States is characterized by 120-volt line-to-neutral differentials, 208-volt line-to-line differentials with an excitation frequency of 60 Hz. Represented as a function of time, these waveforms almost appear identical, only the degree of phase shift distinguishes one waveform from another. Represented as phasor equivalents with phase L1 assumed to be the reference, L1 in black would be 120 volts at an angle of 0 degrees, L2 in red would be 120 volts at an angle of negative 120 degrees, and L3 in blue would be 120 volts at an angle of 120 degrees. Several equally relevant observations can be made using either the plot of voltage as a function of time or the phasor representation. It can be said L2 lags L1 by 120 degrees just as easily as it can be said L1 leads L2 by 120 degrees. Similarly, it can be said that L3 lags L2 by 120 degrees just as easily as it can be said L2 leads L3 by 120 degrees. It can also be said that L1 lags L3 by 120 degrees just as easily as it can be said that L3 leads L1 by 120 degrees. In summary, each waveform exhibits a relative phase shift of 120 degrees with respect to the other waveforms. Given L1 is established as our frame of reference, we can state L1 peaks, then L2, then L3. When discussing phase sequence, it's helpful to remind ourselves that these waveforms are repetitive in nature. When extended for another cycle, the same sequence repeats itself. L1 peaks, then L2, then L3. It should be noted that waveform L1, our initial point of reference, needn't always be considered the reference, and other points of reference can be employed. Consider L2 in red as the reference. Represented as phasor equivalents with phase L2 assumed to be the reference, L2 in red would be 120 volts at an angle of 0 degrees, L3 in blue would be 120 volts at an angle of negative 120 degrees, and L1 in black would be 120 volts at an angle of 120 degrees. As previously, using the plot of voltage as a function of time or the phasor representation, the sequence of these three waveforms can be determined. Given L2 is established as our frame of reference, we can state L2 peaks, then L3, then L1. When extended for another cycle, the sequence again repeats itself, L2, L3, L1. Given the repetitive nature of these waveforms, it should be noted that the choice of reference has not changed the phase sequence, only the starting point within the same sequence. Finally, consider L3 in blue as the reference. Represented as phasor equivalents with phase L3 assumed to be the reference, L3 in blue would be 120 volts at an angle of 0 degrees. L1 in black would be 120 volts at an angle of negative 120 degrees, and L2 in red would be 120 volts at an angle of 120 degrees. As previously, using the plot of voltage as a function of time or the phasor representation, the sequence of these three waveforms can be determined. Given L3 is established as our frame of reference, we can state L3 peaks, then L1, then L2. When extended for another cycle, the sequence would again repeat itself, L3, L1, L2. Given the repetitive nature of these waveforms, it should again be noted that the choice of reference has not changed the phase sequence, only the starting point within the same sequence. When we compare these three different analyses, you'll note the cyclical behavior of three-phase AC demonstrates that black-red-blue is the same as red-blue-black, which is the same as blue-black-red. This is to imply that phase sequence for a three-phase AC distribution system is fixed and unalterable, where the relationship of L1, L2, and L3 is determined well in advance by the physical construction and rotational direction of the generator producing three-phase AC. Unless you are the generator, you have absolutely no influence over the phase sequence of a three-phase AC system. This being said, at the point of use, a technician can apply the different phases in whatever manner they deem suitable for the application in question. As detailed in the Rotating Magnetic Field lecture, available at the Big Bad Tech channel, We learned that three-phase AC establishes a rotating magnetic field in the stator, which the rotor follows with an established rotational speed and torque. As a summary of the process, when voltage at a particular pole peaks, it establishes a magnetic pole which the rotor follows. Consider a three-phase AC motor wired in the following fashion. Phase L1 is landed at terminal A, phase L2 is landed at terminal B, and phase L3 is landed at terminal C. Given the previously established phase sequence, it can be said that as L1 voltage peaks, it establishes a magnetic pole at terminal A. Then as L2 voltage peaks, it establishes a magnetic pole at terminal B. Then as L3 voltage peaks, it establishes a magnetic pole at terminal C. And the process repeats itself, ABC, ABC, establishing counterclockwise rotation. If phase L1 gets off the bus, and L2 and L3 each move forward one seat, and L1 gets back on the bus and takes a seat in the rear, really not much has changed regarding the sequence, only the starting point within the same sequence. As L1 voltage peaks, it establishes a magnetic pole at terminal C. Then as L2 voltage peaks, it establishes a magnetic pole at terminal A. Then as L3 voltage peaks, it establishes a magnetic pole at terminal B. And the process repeats itself, CAB, CAB, again establishing counterclockwise rotation. Similarly, if phase L2 gets off the bus and L3 and L1 each move forward one seat, and L2 gets back on the bus and takes a seat in the rear, again, really not much has changed regarding the sequence, only the starting point within the same sequence. As L1 voltage peaks, it establishes a magnetic pole at terminal B. Then as L2 voltage peaks, it establishes a magnetic pole at terminal C. Then as L3 voltage peaks, it establishes a magnetic pole at terminal A, and the process repeats itself, BCA, BCA, again establishing counterclockwise rotation. Really, the only change in behavior for this system at the point of use occurs when any two phases swap seats on the bus. Consider L1 in seat B and L2 in seat A. Given the previously established phase sequence, it can be said that as L1 voltage peaks, it establishes a magnetic pole at terminal B. Then as L2 voltage peaks, it establishes a magnetic pole at terminal A. Then as L3 voltage peaks, it establishes a magnetic pole at terminal C, and the process repeats itself, BAC, BAC, establishing clockwise rotation. This is opposite to our earlier observations and critical to applications such as reversing motor starters, in which a motor must operate in both the forward and reverse direction. Simply by swapping any two applied phases, our motor will rotate in the opposite direction. You'll find similar clockwise rotational behavior with L1 landed at A, L2 landed at C, and L3 landed at B, where the magnetic pole established by the stator rotates from A to C to B and back again, ACB, ACB establishing clockwise rotation. Finally, you'll find similar behavior with L1 landed at C, L2 landed at B, and L3 landed at A, where the magnetic pole established by the stator rotates from C to B to A and back again, CBA, CBA establishing clockwise rotation. The larger point being that phase sequence established by a three-phase AC source between L1, L2, and L3 is fixed and unalterable. However, they can be applied at the point of use in any manner deemed suitable for the application. Wired in one fashion, a motor would drive a conveyor belt forward and send an elevator up. Wired in another fashion, a motor would drive the same conveyor backward and send the elevator down. Understandably, a user should have some idea of the phase sequence prior to wiring up a motor, as it is a generally recommended practice to avoid driving a conveyor backwards when you press the forward button, and it kind of sucks to have an elevator go up when you're on the top floor or down when you're on the bottom. Oftentimes, primary wires might lack proper labels and might not use identifying colors above a certain gauge. A user might be presented with three otherwise indistinguishable black wires, each with the same line-to-line differential between them, and be left to simply guess the phase sequence. An extremely easy solution to this problem is to first display the waveforms on an oscilloscope to determine the phase sequence. The problem is, not everyone has an oscilloscope, not everyone knows how to use an oscilloscope if they have one, and even if you have one and you know how to use it, which I'm certain you do, using an oscilloscope takes some time and effort.